30 seconds. Okay, time is well up. Let's have a look. Gail, do you mind handing me the question? I can do it. Thank you. So let's look at number 1 here. A projectile is launched horizontally. So it goes this way. And it travels for 0.7 seconds. And its distance here is 50 meters. What's the speed here, V? So if you just use the distance, speed, time triangle, the speed will be 50 over 0.7, which is 500 over 7, which is, what is it? 71.4 meters per second. What is the vertical distance here, SY? So S equals UT plus a half A T squared. What's that? What number is that, please?
2.4.
So the H is 2.4.
How can we know it's from rest?
Because it says it's launched horizontally. There's no vertical. And then lastly is before it's launched, it accelerates from rest. What's the acceleration? And they tell us it's from rest. And the V we calculated. The A we don't know. T we don't know. The S we do know. And we want the A.
Where is this is this?
Horizontally.
Well, I mean in the this.
Oh, that it goes like this? Because they say projectile.
But projectile, it can this way.
Yeah. Projectile can be like this.
But
Can be like this.
This is.
Why is it this? Because it says horizontally. Yeah. If Ben, if they didn't say horizontally, then it would be like the top. Okay. What will give us the A here? V squared equals U squared plus 2AS.
2.4.
Hmm?
The ice is 0.4.
Yeah. It says it's 0.4.
Oh, it's still.
Yeah. No, just to be clear, Gail, what they're saying is for this part of the journey, it started at rest and it was fired out of it like of a cannon, you know? Yeah. So they're saying that this part here is 0.4. Yeah.
Well, I see 0.
There, Ben, I just drew it. Like the ball is inside of something here, and it's fired out.
So
That's 0.4. This.
what mean? It means what?
They want the A in here. In here. Just in this part.
How to calculate?
Well, here it is here. U we know, V we know, S we know. So what's the A here, Gail?
It's 9.3.
You don't like this, the two of you.
So it's minus or
Oh, it's plus. Because it's going right. This A is for the right. It's for like this.
Where is open
Where is 0.3? Ah, the formula I used was V squared equals U squared
A?
plus 2IS. Is this okay? Not okay. Hard?
can I use the y
The Y distance.
for the number 2? So I don't know it's from the rest. I know it.
Read carefully. Yes, yes. Will we do the next question? It's 3 marks, 3 minutes. Here you go, go. Okay, time up. Thank you very much, Go. Let's have a look at number 2. Were you able to get it? So you have a rubber ball. Its height is 1.5 meters. It falls. It loses 0.177 joules of energy. What's the mass of the rubber ball? Oh, yeah, so actually, sorry, their English is not clear, but what they're saying is the potential energy is 0.177. So mgh is 0.177. What is the h then? No, sorry, m. What's the m then?
0.01.
Yeah?
It's
What's the kinetic energy? Answer 0.177.
No.
Yeah. If the process of transferring energy from kinetic before the collision to kinetic after collision is 8% efficient, determine the maximum height to which the ball bounces. Now, that's a difficult question, and before you continue, I have a guess at what the answer is. I think the answer will be 1.5 times 0.8 squared, I think. Now let's calculate. Actually, can you calculate that? I just want to see what it is.
0.96.
Okay, let's see. 0.177. Okay. So when the ball is here, its kinetic energy is 0.177. Okay, that's when it's going down. When it hits the ground and goes back up, it has only 80% of this. So how much is that? What's that?
96.
No. 1.77 times 0.8.
0.8, so 1.142. 0.142.
Joules. Okay. So, a half m. Sorry. So, mgh up here must equal 0.142. So if I divide, what do I get?
1.45.
1.45. No, my guess was wrong. Yeah.
Because I cannot check it.
Are you sure, Ben? Well, what did you get, Gavin?
It is 9.65 and 10 to the power of 3.
What? Are you sure?
Oh yes,
What is it?
it's true. But you couldn't use 1.5. You just 0.01.
Sorry. The mass is 0.01, isn't it? I'm so sorry. It's 0.01. 9.8 h equals 0.142.
0.02. It's 1.45.
Yeah, that's what Ben said. 1.45 meters. Okay, sorry. So my guess was wrong. The guess was wrong.
You say it's deep.
It is a bit difficult for 1 mark.
Why,
It's only 1 mark, you know.
why is 18% it's given?
Yeah, it is.
Uh,
Oh yeah. It has to be. Yeah. How else? Yeah. Oh, I see. Well, because if it was 100%, the answer would be 1.5. If this was 100%, yeah, the answer here would be 1.5. It'd be the same. It'd just keep going like this.
Yes. So if it's 1.5 times 0.8 is 1.2.
let me think about this. Can you look? So we try and think of a formula. So here it has potential energy, and that becomes kinetic energy, but then on the way up it becomes kinetic energy times efficiency, like 80%. So kinetic energy times efficiency equals potential energy. So that's a half mv squared times that equals mgh. So the h is this over mg.
Yes.
Yeah, so the maximum height is the kinetic energy over mg times efficiency. Yeah, it's not really a nice formula.
But just we get.
Yeah, yeah.
So
The reason I was thinking about the square in my guess is because I was thinking about this.
Why?
I don't know why.
We don't.
Just a feeling.
Okay. We don't need a square like we.
I know now. It's just a guess. A feeling, Ben. A feeling.
Okay.
Right, the next question is 4 marks, 4 minutes. Here you go.
Maybe you think too hard. Too many.
I know I think too hard,
Just
too many
1
times
mark.
for 1 mark. I know I do, Ben. I know I do.
Yes.
Yeah, that's what you have.
Just I think is
Yeah?
K L.
Oh, stop. No, young modulus.
Oh, it's string.
Pascal.
Yeah, it's Pascal.
Oh.
Stand.
Okay, let's have a look now. You can. Okay, I could get it. Yeah. Right. What's stress then?
A material is the force acting on the material per unit of cross-sectional area.
Correct. Good. Right.
So what's meaning by this, really?
Force per area.
Force per.
Okay, a thin metal wire of diameter millimeters used to suspend a load of 250. What's the stress? Okay. Stress equals force over area, which equals 250 over pi. 10 minus 3 over 2 squared. And what is that?
3.18 times 8.
Unit?
Pa.
What? No, say that properly. No, don't.
Huh?
The full name.
Pascal.
Thank you, Pascal. How much is the next one? 4 marks. Ben, I'm sorry, but nobody says pa. Everyone always says Pascals.
Okay.
Okay, here you go again. 4 marks, 4 minutes.
Oh, it's old. Like a material stored reduced something, reduced the current gases, reactants. Material, like just definition. No, it is.
You only have Ohm's law.
You didn't write down the definition of an ohm.
Is that
Ohm
Ohm's law?
isn't a resistor.
Yeah,
The unit
of resistance.
the unit used is the ohm,
Yeah.
but they ask ohm, so
Yeah, the definition of an ohm.
so
1 ohm.
just
Oh, here.
wait.
Get that.
We over
You can use this to help you remember the definition.
we per current
Oh, not too bad. Not too bad.
vector per current
Vector per current?
charge.
Charge per current? Something per current?
One
Taco chips per current?
this lunchtime choose the my shawarma.
Shawarma good.
And I got the 7
Good.
again. It's free.
Good job.
1 volt of electrical energy was converted.
That's it?
To 1 mark. I think I can give out the definition.
Try. Try.
I just understand the meaning and use own word. Use own word.
Of course.
But I think
It's good for your English.
if I use own word like very simple, the complete things I can use simple word.
Simple's okay.
both positive and negative. Not only this, I mean,
Yeah, you can have negatives too, yeah.
this.
Yeah. Okay. 4 minutes, wasn't it? Let's have a look. Now, Ben, you had trouble remembering the definition for ohm. Okay. Let me give you some tips. A tip. Okay. If they ask you for a definition like this, think of the simplest formula that uses ohms. So the simplest one I can think of is VIR. Okay, so that means OR is V over I.
Yeah.
Okay, so OR is ohms, V is volts, and I is amps. And this here is per. Okay, so you could say 1 ohm of resistance. Whoops, I spelled resistance wrong, didn't I?
Yes.
2 S's. Resistance is when 1 volt of potential difference is converted into a different form. Per unit amp of current. Yeah. Right, next. What is the resistance? Okay. It's 3, is it? Okay, easy peasy. And lastly, the sketch. Oh, okay.
Current.
So V, well, you know what, I'll be a bit more. Potential difference V, current A. All right. And yes, go, they wanted the positive and the negative. Now, it doesn't really matter because it's the same picture if it's backwards. If you have a lamp, like this lamp here, okay, and you turn it around, nothing really changes. So let's draw this. So what happens? Well, here it's ohmic, and here it's ohmic. When the voltage gets too big, what happens to the resistance for the lamp? Do you remember? Does it get more resistance or less resistance?
More.
It gets more resistance. So what happens is the graph goes like this, and then it'll go like this. So you could say it's ohmic from here to like here, and then outside here it is non-ohmic. Non-ohmic.
These ones are.
No, it's not.
So both for all. Is PP or is PP?
PD.
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 What's PP?
Police department.
Please apart.
No, sorry. Potential difference. Not police department. In English, PD has 2 meanings.
Oh.
It can mean potential difference, which just means voltage, or it can mean police department.
Or police department.
Police station.
Oh.
Yeah.
Okay.
So why Irish call PlayStation card?
That's the Irish name for it.
My friend was seek for help in the pub, and he asked the waiter, "Where is the place station,
Yeah.
and the man don't understand.
Yeah. Because we don't use that name.
But you should know, like, PlayStation, bus station. You know the word.
Was he Irish?
I think so. Okay.
Okay.
You say please defund.
Yeah. Well, it's not police department. It's potential difference. Yeah. How many marks for the next one, Gav?
3.
3 marks, 3 minutes, off you go. You have 1 minute and 15 seconds. Yes? "30 seconds. Oh, this is a hard one, I see. Not even going to try.
I don't know what is T. Unit.
Tesla?
Yes.
Maybe I don't have. I missed this lesson.
I think you missed many lessons.
I even don't have memory of T.
Okay.
The magnet.
Come here, let's do it. Thank you.
Is that about finger?
Huh?
No? Magnetic field.
It's that chapter, yeah.
That makes
A wire of length 2 carries current of 4 in a magnetic field after which way? Okay, yeah. So we got a wire of length 2. So the current is this way. No, from east to west. This way. The magnetic field is this way. And they want to know what direction is the F.
Where say the B is this way?
From south to north.
Oh, sounds no. So
Now, which? It's the left-hand rule, okay? So, B is up, I is left,
in.
so F is in. The answer is like this.
it's 3D.
I liked it. In.
Hmm?
This symbol means in. Ah, you really don't remember. Do you remember what's the symbol for out? Out of the page.
Hmm?
Ah, that's in and that's out.
Oh yeah.
So that is the magnetic field
Yeah.
direction. That's
F. The force.
force.
Yeah.
And what is I?
Current.
Does that say that's force?
B. Up. I. Left.
Oh, that's I.
Yeah.
So
Yeah, exactly.
that's force.
Exactly.
Ah.
Right, what is the force? So the formula for the force is Bill, which is 6 times 10 to the minus 3 times 4 times 2, 8, 8 times 6, 58. Isn't it?
Isn't QEB?
No, BIL.
Why I remember QEB?
That's a different lesson.
Huh?
That's a different lesson.
It's the same.
A different question. Yeah? 52, is it? My goodness, what the heck is 48? 48 millinewtons.
No, it's 4.8 and 10 to negative.
Or 48 times 10 to the minus 3.
Milli.
Milli. Oh. So the next one you need to use the right hand grip rule. Remember I asked you to draw this in your book and you're like, oh Stephen, why do we have to draw it? And I said, well maybe they'll ask you to draw it in the exam. So you have the current that goes this way and the magnetic field around the current is with your fingers. So it's like this.
Oh, like this.
This one I asked you to draw. Yes, Ben. Oh, no, sorry, I misread it. They said draw it into the page, so they want you to draw it like this.
2D.
2D into the page. This is the I. So it'll be this way, isn't it? Into the, yeah. No, your thumb's the wrong way. Into the page, yeah.
So the right hand rule is that was curved. That's
For curved, yeah.
That's curved.
Yeah.
Current is in.
It says current is in, yeah. See? Look, current into the page. See? Into. Okay. 3 marks, 3 minutes. Question 6.
Oh, it's pin hole. Oh, yeah, I know hole. But it's pin hole.
In.
Oh. Okay.
Pinhole is just a really small hole. Tiny little hole.
Oh.
Like a needle.
Needle.
Yeah, you put the thread in the needle. See here, Ben. That's like a pinhole. That little hole there. See, it's a useful phone. Very useful.
Oh, yeah, it's like this part, like it's three definitions. Actually, it's three definitions.
I know, Ben, I know. Come here, go. Time's up. Let's have a look. So, no, they're not like definitions.
Let's say
This is easy. Look. You have a small pinhole, okay? What happens if you make the pinhole bigger? So the wave comes in and comes out, okay? If you make the hole bigger, you get this. That the wave spreads out more.
so I just say the wave spread.
You could say the wave spreads out more, yeah. You could say diffraction is wider. Now, the next question, okay? The next question is a little bit hard, so let me try and help you with it. So in part B, what they do, they keep the hole the same, but they change the wave. So firstly, it is red. And then secondly, it's blue. And the question is, which one, what will happen? Will it diffract more or will it diffract less? It'll be helpful to know the wavelength. So if we think about, do you remember this picture here? High frequency, low frequency.
Yeah.
And in the middle you had visible.
Yes.
And you had red, orange, yellow, green, blue, indigo, violet. Red has a high frequency. No, sorry. Sorry. Red, orange, yellow, green, blue, indigo, violet. A violet has a high frequency and red has a low frequency. So this one here has a low wavelength and this one here has a high wavelength. So if you look at the picture, red has a high wavelength. So here the wavelength is big and here the wavelength is small. So this is like do you get what I'm saying here? What I'm saying is, because the wavelength is smaller, it's like the hole is bigger compared to the wave, because the wave is smaller. Do you get the idea?
Yes.
So, will it diffract more or less? It'll diffract more. So that the blue is wider diffraction. Yeah? No?
Lambda is small, so it's bigger.
Yeah. Because it's like, if you think about it like this, you know, we said if we make the door bigger, we make the wave wider. But do you understand that if I keep the door the same, but make the wave smaller, it's like I made the door bigger, because the wave is smaller compared to the door. You get the idea? Yeah. Yeah? Last part, continue. Now, what do you think would happen if I use white light? What would happen? Well, if you look at the screen, what would happen is this. You get red in the middle, but because the other colours have different wavelengths, like here, the blue diffracts more. So what would happen is you'd have red, and then you have orange, and then you have yellow, and then you have green, and then outside that you'd have blue. So in other words, what you get is you get the rainbow. It goes red, and then around that you'd have orange, yellow. So you get a rainbow from red in the center out to purple at the edge. I should actually, wait, I should write a rainbow as a circle. It's like concentric circles like this. So you could even draw it. You could say red, orange, yellow, violet. You don't like it.
What section is so different?
It's not really. It's just the English is the problem. The next question is 4 marks, 4 minutes. Here you go. Okay, let's have a look now. Did you get it finished, Go?
No, it's the second one.
What did you say for binding energy?
The energy required to hold nucleus
Per nucleon. They said what's the binding energy per nucleon? So what you said plus per nucleon. So you said the energy required to hold the nucleus together per nucleon. Okay, so the next question then is just 1622.27 divided by 206. What's that? What's that, please?
Why is 206?
There's 206 nucleons. Say again?
7.88.
Is that okay? You look confused. Ben? Is it okay? Are you sure?
No.
What's wrong? Look. Look. Is what's the binding energy per nucleon?
Where is the bonding?
There. The binding energy is this.
Which lesson?
Oh! Is it fusion and fission, or the one
No.
before that?
One before the Einstein.
Einstein's equation, yeah. Einstein equation. There.
Oh.
What is AMU?
Huh?
AMU.
AMU, also called U, atomic mass unit, the mass of one proton or one neutron, roughly. Right, go. What did you say nuclear fission is?
Is when an atom splits apart into smaller atoms.
Yeah. Releasing energy. So when a larger isotope, no, let me be super clear maybe. When a larger unstable isotope is split into two or more smaller isotopes, thus releasing energy. I think I should also write in here when a larger isotope is split, and then maybe just put in beside this via collision. So what I mean is you collide with it to break it. It's okay? Ben?
What's been on the bus station? They're usually after two, they will show them. The Irish?
N-O-N?
No, A.
Ah, A-N-N. Yeah,
It's Irish?
yeah. And then the other one you might see is nom, which is like in English min for minute.
I was told that first time Alan was delayed, will be late.
Which one? This one?
Yeah. Because usually English first and Irish,
Yeah.
and then so the bus will late, will not be on time at first time.
No,
I don't know
oh,
about
yeah, no, not And bus is easy. Bus is bus. Yep. Okay, 4 marks, 4 minutes. Be strong, go. Yep. 30 seconds early, Dan. Good job. But I think this was an easier question, yeah? Right. How do you make a step-down transformer? What do you need? Number 1, you need some iron.
They asked me that.
Let's briefly describe the construction of a step-down transformer. What did you do? Oh, that's well, what did you write? Maybe it's okay.
Step down transformer decrease the
No, okay. So, step-down transformer is like this. You have many turns here, and not so many here. Okay. So, the left side, called the primary, has an insulated current AC wrapped around N1 times. Now you don't have to write everything again for the next one. You could just say the right side secondary has an insulated current wrapped around it N2 times, and you need N1 to be bigger than N2.
Oh, structure.
Construction,
No definition.
not definition, construction. You did the same thing as Go.
Very wrapped it.
Wrapped.
Wrapped.
Oh, sorry, there's an or.
Better.
Right. 5,000 over N2 equals 3,000 over 240. So what's N2? 400. And then you could say for the next one, they want the current in the first one, yeah? So you could say I1 times 3,000 should equal I2 times 240. Because I'm saying power 1 equals power 2. Power in equals power out. Because they said it's 100% efficient.
Okay.
So power in equals power out. So what's I1 here?
I use the
Yeah, there's other ways. I1 over I2.
N1.
Yeah, that's fine. Yeah, you should get the same answer. What?
200.
1.2.
No, I think you made a mistake.
200.
No, it should be a small number. Do you say I1 over I2 equals N2 over N1?
Oh, they are positive. They are.
Should be this. Yeah, thank you, Ben. Okay, the next question is 5 marks, 5 minutes. Off you go. Okay, time up. That was 4 minutes. Let's have a look. Thank you. Was it okay? Describe the evidence that's... Ah! So do you remember this one? Yeah. So go ahead, Gail. What did you say? So the question is asking you... Okay, so remember we said that electrons can sometimes be a particle and sometimes be a wave. So their question is, when light hits the metal and releases an electron, do we imagine the light is behaving like a wave or like a particle?
No.
Which? Come on, it's 50-50. Which?
What do you mean?
Okay. Now go, look at me. Go! Look at me. Ben, look at me. So you have your metals. No, cow! I must... Do I look really bad?
No.
She never wants to look at me. I must look terrible. I must look a mess. Right, so you have your metal surface, okay? You have your light. The light comes down and hits the metal, and then electrons come off the metal. The question is, when the light comes down, do we imagine it is a wave or it's a particle?
Wave.
Which is it? No, particle. Because what we're picturing is like this. I'll draw it. Now watch, Ben. What? No, watch. Because remember we said sometimes things can look like a wave and can look like a particle. So let me just plug this back in. Come on, there we go. So when we think of the metal, the electron is trapped. Okay, the light comes down, but we imagine it's like a particle, and it hits the electron and knocks it out like a ball. You know, here's the electron and here's the light, and it goes like that. Yeah. So the answer is a particle, and the reason is we imagine it is like a collision. Do you know what I mean? Yes? Right. Next question. I wonder what you said. Describe what happens to the energy of the light. So what happens to the energy of the light? Where does the light go? What happens to it? You see, afterwards you have only the electron and no light. So what happened to the energy of the light?
Absorbs.
Good. And then what happened?
And the electron will it will provide.
Go on.
Provide the energy power to like the electron move.
Okay, so absorbed by the electron to provide it with, you said two things, Ben. The first one, the energy, or what you said, the power to, we won't say move it, we'll say free it. Also, it does a second thing. Because if you look at the question, how many marks? It's 2 marks. Right, so what's the second thing that it does?
Change the I think
Absorbed by the electron to provide it with energy to free it, and what else does it provide for the electron?
I remember it's like move.
Yeah, so what energy does it get? There we go, kinetic energy. Yes. Good. What? What did you say?
The energy provide actually is the light provide the energy make the electron move.
Good. I will give you 1 mark.
So I need to
You need to write 2 things because it's 2 marks.
move with kinetic energy or free. Okay, free.
Good. point actually. Which mark will I give you? I don't know. I don't know.
Maybe not.
No, I will give you one. Okay. Right. So I see that you have the formula for the next one, Dan. KE equals what was it?
Minus work function.
Oh yeah, but I think the way we wrote it in class was work function equals KE plus HF, wasn't it? No, what way do we write?
HF minus maybe? Oh, plus. Just plus. I think. No.
What was the formula? Oh sure, I have it right here. I could think about it, but I don't want to think about it. HF equals work function plus KE. And what do they give you? They give you F, and we know H. And we know the work function. Oh, so they just want this. So the KE equals HF minus the work function. The H, whatever it is, times 3 times 10 to the 15 minus 4. And don't forget the E. Because the unit is electron volts. Oh!
The 4 is
Stop! This is the kinetic energy. But they also want the kinetic energy in electron volts. So you have to divide the answer by E.
Do we need multiply E?
Yeah.
4?
Yeah.
Why?
It's not given like 4
Yes, it is. 4 EV. Have a look.
So we need.
You make it joules and then make it EV again.
Why? Why?
Look. Look. Okay. This one here is to make it joules. Okay. And then this one here is to make the answer EV.
EV tens EV multiply E equals joule.
EV multiplied by E makes joules, yeah. Yeah, so yeah, EV to joules, you multiply E, and then backwards, you divide E.
So it's
What you get?
4 tenths or the total? Not just 4 tenths.
No, just the 4.
I can't find the university.
I don't know if it's on this calculator. Show me your lid. Show me the lid. The lid. No, just the lid. The lid. Just the lid. The, yeah, the lid. This thing. I just want that. Let me see. Oh, there's nothing on it. Okay. Well, I don't know what button is for E.
There was shows E, but they have E power.
Oh, not this E.
And there has a E, but I don't
Not
know.
this E. It's a different E.
It's 1 plus is.
What is it?
I know finish.
Ah.
So we have E's number actually.
It's in the... Go. It's at the front of the exam. E and H are at the front. First page. First page.
Oh, 1 plus is so 2 times
It's minus.
Don't need the minus here.
It's 1 4 6 2 times minus 19. And the total. There are 1 4 6 2 times 2 minus 19 equals 8.4 times 10 minus 38.
Well,
What? No, I think you need another bracket. You need more brackets. There we go. 8.397. 8.4.
What?
You needed a bracket at the end for the divide.
Oh. Oh yes. Yes. Yes.
Okay.
Oh, because this is true, so and they gave us the EV. Oh, it's
Ah, it's great. I like it. Okay, look. We'll, yeah. You're finished or you have class after this?
yes.
Which? Finished or class? Are you finished or do you have class
No,
now?
no, go.
Home.
Home. Finished.
Yes.
Fine. And you finish your lab report tonight.
Yes.
Tomorrow night.
I'm ready.
Ah, tomorrow night.
I'm ready.
Tomorrow we'll do maths. Friday we'll do physics.
Yes.
Okay. Summer, if you're watching this video, we all miss you, don't we?
No problem.
What?
If they,
If he watches this, we all miss you.
if he watch the video, I can't believe he will watch. He will spend 2 days to watch.
He might. Summer, we miss you.